Hello all and welcome to Lab 2 where we're going over trajectory. The purpose of Lab 2 is to observe the motion of an object, in our case a paper ball, with both x and y vectors, and to showcase the force of drag approaches the force of gravity as time passes. This is called terminal velocity. It's important to note Newton's first law of motion as described here, and Newton's second law of motion. Additionally, we'll be using the tracker model as our experimental values and the GlowScript computational model to showcase our graphed values. We'll also be going over the concept of drag. We're considering that accounting for drag will make the model more accurate, and that if the net force y is 0, then the object has reached terminal velocity. If the paper ball is going to be considered a perfect sphere in this experiment. So the concepts to note are that the force net divided by mass is going to be our acceleration. The velocity final is going to be equal to the velocity initial plus acceleration times time. The force of gravity is going to be equal to mass times gravity in the negative y direction. And that drag is going to be equal to negative b times velocity squared times velocity hat. Our initial conditions are that movement was recorded after contact with the paper broke, therefore there was no extra recorded acceleration. The paper moved strictly horizontally and vertically. There was no movement in the z direction. There was a meter stick in the background to make sure that our measurements were accurate, and that the camera was stationary throughout filming. Once we clicked record, we did not touch the camera afterwards. Our frame of reference was constant. And then our b value is going to be 0.47 because we're considering the paper ball as a perfect sphere. The experiment itself is that we chose to throw a piece of paper balled up in a sphere to determine how the force of drag affects the trajectory of a body in motion in both the x and y directions. We did this by creating two models, one with only gravity affecting our ball, and one with both gravity and drag, in our case air resistance, since the ball is thrown through the air. Then we looked at their similarities and their differences. Here's the GlowScript models. From these graphs it can be seen that as time goes on, the model becomes more accurate. The model specifically being the drag and gravity model. And the b value of 0.47 seems to be doing alright, and since the ball was semi-spherical. We can see that the yellow line is almost exactly the same as the blue line, our yellow line being gravity and drag, and our blue line being the tracker. And in this case, the yellow line becomes more accurate as time goes on, being more accurate than the red at the very end of our model. Here is our program. We can see some things of note are that our gravity is 9.8 and that our b value is 0.47. Here is our drag equation. Something to note here is that this is multiplied by 0.5, as the resource I saw showed that it should be multiplied by 0.5. The resource given did not say that. If you're not considering 0.5 to be more accurate, then this b value would be half of what it is. Here's the force net equation. Here is the velocity update equation, and then the velocity hat needs to update after this. The ball position update function needs to be after the velocity update function. One more thing of note is that the mass is equal to 1, although our paper mass should be 0.0045 kilograms. It's 1 because if you use numbers as small as 0.0045, it becomes less accurate as the program cannot do computations that small. When running this program, we can see that the velocity initially is pointing up and to the right, and then as time goes on, it goes downward more and more, and then our drag gets larger as our velocity gets larger, while our gravity is constant. Looking at our y direction, the velocity as y goes on seems to be decreasing, with our acceleration being, it starts off more negative since drag and gravity are acting in the same direction. Then as the ball reaches its peak, the only force acting on it is gravity, and so it's exactly 9.8. And then as time goes on even further, the ball starts heading downward, and so the force of drag is acting opposite to the force of gravity. Looking at our analysis of the net force, it can be shown that the tracker and gravity graphs are different, so there must be another force, this being drag, and that the gravity and drag model is more accurate to the tracker model. Both models use the velocity update formula, and the value of b is 0.47 seems to be accurate. The system and the surroundings. The system is the thrown paper ball, with the surroundings being the Earth and the air particles, the initial conditions being that no force applied was acting on this, but the initial velocity x and y are some value greater than 0. The differences in similarities and errors being that the differences is that the net force decreases for both the tracker and drag while the gravity is consistent. The similarities being that both tracker and drag models approach a linear y value near the end, this being constant velocity. There being the parallax error, and that there's also possible human error on tracking the paper ball. The differences is due to drag from the air particles imparting some force on the ball as it pushes the air particles out of the way. It approaches a constant velocity, meaning that it approaches terminal velocity. Parallax is from a meter stick in a different z-plane, and that drag should be considered when examining our object's trajectory is what we have considered fully. The what-if questions ask and show that the model with drag predicts that if the ball kept falling, it would reach a state where there's no net force in both the x and y directions and would be at free fall at constant speed. If the object was thrown with the same velocity, v hat, but only in the positive y direction, the ball would take longer to land, as although drag would affect it more than the initial ball, the increase in velocity and therefore momentum would affect it more in total. However, if there was the same y velocity as in the original experiment but no x velocity, the ball would land at the exact same time as every force in the y direction was the same as in this new model as the old. And here's our video.